recap. Section 9.2 is matrix notation and Gauss-Jordan elimination. We want to learn about matrices, augmented matrices. This will be related to a system of linear equations. We want to learn how to solve a system of linear equations using Gauss-Jordan elimination and reduced row echelon form. So I will show you what these look like. Okay? So let's just have a conversation. So let's have a little conversation. Okay? Here, this notation is called a matrix. Okay? Notice that whenever you have it set up this way with these numbers inside, this is called a what?
Matrix.
A matrix, right? You've seen something like this when you watch the movie The Matrix. At the very beginning, when you have those numbers going up and down, this is a matrix, right? It's a rectangular array of numbers. That's the technical definition. We'll define it soon. But going across, what is this called? Row. Yes? A row.
Right.
So we have to be able to identify that. This will be called row 1. This is row 1. We'll typically write R1 for row 1. This next one is called row 2. What will we write for that? R2. Doesn't have to be in parentheses. I'm just putting that as an aside to let you know. What's the next one called? Row 3. Good. How do we identify it? R3. Good. Now, what is this vertical? Columns, yes? This is column what? 1. This is column 1. We don't have to write C1 because we won't do what's called operations with those, but we need to know it is column 1. What is this one? Column 2. The next one? Column 3. The last one? Column 4. Now, in this matrix, how many rows do we have? 3. How many columns do we have? 4. So we say that the size, I say size, your book says order. Some people say dimension. Your book says what? I say size. I say size. Your book says order. So I'm going to, if you hear me say size, I mean order. If you hear me say order, I mean size, right? Some people, you'll hear people say dimension. I won't use that a lot in this course at all. But when you hear the dimension of a matrix, people are talking about the size of the order, okay? So the size we identify is the rows by the columns. We never multiply it out. We just say the rows by columns. So the size of this is 3 by 4. It's 3 by 4. Now, the elements or the entries, we call them elements or the entries, are the numbers that appear inside of the matrix. How many entries do we have here? 12. You got it. I have 12. They're called entries or elements. Entries or elements. Good morning. Now, the subscripts in general for what size is this matrix? Or what's the order? 3 by 4. Good. This is a 3 by 4. That's the order or the size. The subscripts tells us where the entry is located. Remember, rows by columns. So this means first row, first column. This means Good. This means, oh, we can say it together. This means,
second row, third column.
Good. This means,
Second row, second column.
This means,
First row, fourth column.
This means,
First row,
This means,
third row, first column.
This means,
Second row, first column.
and this means.
Third row.
Very good. Okay. So I'm going to call this smiley face here because I don't want to write it over again. In smiley face, I want you to identify A12, A23, and A34. I'll give you 1 minute to fill this out. Check in with your neighbors whenever you have it to confirm. A12 means we want the entry in the first row, second column. Good. What is it? 6. Very good. 6. Ah, yeah. First row, second column. First row, second column. So really what you're doing is you're going first row, second column, where they intersect is where you're grabbing it from. Make sense? No? All right, good. A23, what is it? 2. How did you find it?
Second row, third column.
Second row. That's not a row, that's a what? Column. Second row, third column, so right here. You got it. Very good. Last entry means we want the entry in the third row, fourth column. Third row, fourth column, what do we get? 4. Very good. What questions do you have? None? Okay, all right. So let's define everything formally. So now you know how matrices work right now in terms of the notation, how to identify the size or the order, how to find the entries or the elements, right? Okay, so let's formally define it. A matrix. You want red or blue? Which one? Blue. A matrix is a rectangular array of numbers called, didn't they ask that question in the matrix? You want the red pill or the blue pill? I just thought about that. Ha. Okay, a matrix is a rectangular array of numbers called, what are those numbers called? Entries. Good. Or elements. Good. Of the matrix. The blank or blank of the matrix is determined by the number of rows, by the number of columns. The order or the size. Very good. Some people call it what? Say what? Dimension. Will I call it that? No, but that's okay. All right. So, example 1. We normally reserve capital letters to name matrices. So you'll often see it called capital A, B, but we reserve capital letters to name the matrices. So B is the matrix consisting of rows 8, 1, 3, 0, rows with entries 8, 1, 3, 0, 6, 7. I want you to determine part A, the order of B, B, the value of B12, C, the value of B23. I'll give you 1 minute. Okay, what's the order of B? Yes, it's a 3 by 2. Because that means we have 3 rows and 2 columns. You got it. What's the value of B12? B12 means when the first row, second column, you are correct. It is 1. First row, second column. What's the value of B23?
Undefined, something.
Undefined, so in this case, we say none.
None.
I thought it was like a trick question.
It was. No, it was. And very good of you all to identify that there is no value or it's undefined. It's undefined because I asked you to identify the entry in what row? Wait a minute. Second row, third column, but there's no third column, right? So there's no value. Excellent job. Excellent. Okay, now let's introduce more information. And I put it side by side because I want you to be able to identify what's called the standard form of a matrix and be able to put that matrix from standard form to augmented. Okay, so let's talk about a system first. A system of linear equations is in what's called standard form. We are saying that the system, right? So, for example, the system that we talked, the examples that we did from section 9.1, where the size was 2 by 3, y'all making me nervous. Is there something crawling? I'm distracted. Okay, so I had to pause the video and all the things, okay? We don't want that in the recording, but glad everybody's good. Okay, so a system of linear equations is in standard form. The system, right? Do we say the matrix is in standard form? The system of linear equations is in standard form when each equation has been simplified with its variables on the left-hand side and its constant term on the right-hand side of the equal sign. Okay, read it one more time. A system of linear equations is in standard form when each equation has been simplified with its variables on the left-hand side and its constant term on the right-hand side. Okay, so for example, given this system, negative 2x, I'll highlight it. Given this system, negative 2x plus 3y equals 13, and 4x plus 2y equals negative 18. Is this in standard form as it is given?
Yes.
No. No. In standard form, what does it say?
Variables on the left.
The variable's on the left, so that's a check, yes.
On the right.
The constant's on the right, that's a check, yes. So far so good, but what else? It has to be simplified. So when we look at which equation, 1 or 2? 2. 2 is not simplified because all of them have what? They all have what? Say it loud. I heard it. They all have a 2 in common here. So that means we have to simplify equation 2. So simplifying equation 2, equation 1 remains the same, negative 2x plus 3y equals 13. Equation 2, when you divide each part by 2 here, that becomes 2x plus 1y, or just y, equals negative 9. So this system is now in standard form. So, again, for your system to be in standard form, each equation has to be what? Simplified, yes? Each equation has to be simplified. Then you must have your variables on the left-hand side and your constants on the right-hand side of that equals. Yeah.
Why did we take the top equation?
Was it simplified? Say it, what, Renatia?
They're not divisible.
Oh, okay.
Right, you got it. They don't have anything in common. Very good.
Gotcha.
That's the same thing she said when she said it's not divisible by something. So you're good. What other questions do you have? So this system is in standard form here. Now, let's provide another definition. The augmented matrix bless you. You're welcome. The augmented matrix of a system of linear equations written in standard form. So that means whenever you have a system, you're starting out with the system that is in standard form in order to be able to write its augmented matrix. Okay? The augmented matrix of a system of linear equations written in standard form is a matrix consisting of the coefficients of the variables listed in their respective positions with an adjoined column of the constants of the system. Sounds more difficult than it actually really is. Let's do an example. Here, we took the system given in example 2A in standard form. This is what we started out with right here. If we want to put this system, if we want to write the augmented matrix for this given system, this is the augmented matrix. We took the coefficients of each row. We put them here. We put the coefficients of equation 2 in the second row. We put a vertical bar here to separate the constants from the variables. So that means this column represents what variable?
X.
X, you got it. The second column represents Y, good. And the last column represents your constants, good. You got it. So now we took the system that was in standard form and we wrote the augmented matrix. We good? Okay. You need a second? All right. So let's define a new term. A matrix is in row echelon form. A matrix is in row echelon form. Sometimes I'll write R, capital REF. A matrix is in row echelon form if each of the following is true. Each one of the following things have to be true. The first non-zero entry in each row is 1. The first non-zero entry in each row is 1. We call this a leading one. So again, the first non-zero entry in each row is 1. That one is called a what? A leading one. Very good. Every entry below a leading one is 0. And each leading one appears farther to the right than the leading ones in the rows above it. Is too much being said?
No.
Do you need to visualize it? Yeah? Okay. Let me say this last one and then I'll put something to visualize it. All rows consisting of entirely zeros, if there are any, appear at the bottom. So let's talk about this. I'm going to give you a visual for it. Okay, so The first non-zero entry in each row is 1. So we start in row 1. This is a 1. This one is called a leading 1. It's a leading 1 for row 1. Yes? So we have that. It says every entry below a leading 1 is 0. So everything below this leading 1 is 0. Let's move to row 2. The first non-zero entry is what here? This is 0, but the first non-zero entry is 1. This is a what? Leading 1 for row 2, yes? So far so good. Now it says everything below this should be, we move below, is 0. Now we move to row 3. We have 0, 0, 1. So the first non-zero entry in row 3 is 1, and this is a leading 1. You got it. We don't have anything below it, but that's fine. So this matrix is in what form? Row echelon form. This is an example of a matrix in row echelon form. Okay? Now, if I decided to just add another row of zeros, is this still in row echelon form? Yes, because what? That's right. All rows consisting of entirely zeros appear at the bottom. We good? What questions do you have? Okay, so now I'm going to ask you to determine if the following matrices are in row echelon form. If not, explain why not. I'll give you 2 minutes. All right, part A. Is the matrix in row echelon form?
Yes.
Oh, how did you figure that?
It has a leading 1.
Has a leading 1.
Underneath 1 is 0.
Underneath is 0. Then you move to row 2.
It's a 1.
So 1. Good. Then below is, then we move to row 3 is say 1. Now let me just give you another term. Whenever we have a matrix like this, and what kind of matrix is that? What kind of matrix is this? You just learned the term on the previous page. Augmented matrix. Let's use our words. If you have an augmented matrix, yes? If you have an augmented matrix like this, and this in row echelon form, or whenever you just look at a matrix, an augmented matrix, that is called your main diagonal. You won't use that a lot in this class at all, but just because it's good information to know, you might hear some people say, hey, that's your main diagonal. That's your main diagonal. This column is X, this is Y, this is Z. Yeah, very good. Okay. B. Is it in row echelon form? No, wait a minute. Why not? Say what?
The rows consisting of zeros, not the bottom.
Yeah. The row of zeros should be at the bottom. Very good. So in particular, when we look at row 2, that should be at the bottom, but it's not. Okay. C? No as well? Why? I can't hear you. There is not a leading 1. The first non-zero entry in row 1 and row 2 are not leading 1s. You got it. So, no, the first non-zero entries in rows 1 and 2 are not leading ones. Okay? Very good. So in particular, we looked at these two. They don't work. So those are not in what form? Row echelon form. You got it. Okay? Now, example 4. Given the following, what kind of matrices? Augmented matrices. Construct the system of equations that corresponds to each of the following matrices. We're going to construct the system of equations that correspond to the following matrices. Which one do you want me to go through with you? 1? Okay, so this column we said represents, the first column represents X, second column, good, third column, Z, and that last column is just our what? Constants, yes? That vertical bar means what mathematically we should have for an equation? Equals, yes, very good. So to interpret row 1 as an equation, that is 1x plus 2y. What's the next? Very good. Equals 0. So 1x plus 2y minus 8z equals 0. 1x plus 2y minus 8z equals 0. Second equation translates as, say it again. Good, equals, you got it. And notice that we didn't have to write 0x. Is it incorrect if you write 0x? No, it's the same thing, right? Because 0x is 0. So if you choose to write 0x, that's fine.
What about the 1x from the top? Can you put it as x or?
Yes, you can just put that as x. Absolutely. Instead of 1x, you can write x. And third row, what's the equation? Good, z equals 10. So this is the system of equations for this augmented matrix of order what? Of order what? What's the order? I'm just asking you for extra information because I can. This is a 3 by 3, so you telling me it got 3 rows, 3 columns? 3 by what? 3 by 4 because it has 3 rows and 4 columns, yeah? Yeah? All right. So this augmented matrix has this system of equations that corresponds to it, and we know that the size of the matrix, the augmented matrix, is 3 by 4. We good? Do part B. How much time you need? A minute? Okay. Okay. So, you're given this augmented matrix of order what? Say it again. Of order what? 2 by 3, yes? And then we want to write the corresponding system of equations. Go for it. Good. 5x plus 3y equals 9. Now let's say it together. What is equation 2? Oh, get y'all timing right. Go ahead. It's not that you're incorrect. You're correct. I just need your timing together in sync. Go. Yes. You can say 1x plus 4y equals 12, or you can say x plus 4y equals 12. That's your system. Very good. Okay, so now what we're about to learn is elementary row operations. What you want to keep in the forefront of your mind when you're talking about elementary row operations is this idea of elimination. With elimination, remember you had to figure out how to cancel a variable. So you're asking yourself, if you have the coefficient of x was 5 and you want to cancel out your x term, the next one is x, you have to multiply that second equation by -5. So let's put an image with what I'm saying. Okay? I see that this was cut off when I scanned it in, so let me fix this. This is -9, that's 13. That's 13. And there we go. Okay? So, you'll see a lot of words, but I wanted to put this should be each. I wanted to put this in a table format so you could be able to refer back to it. That's 1, this is 2, last one is 3. Okay? So you can have the operation, what it means in our words, and then have an example to go with it. Okay? So elementary row operations. We reserve capital letters for what? If you need to send a message, go in the hallway. To identify the matrix. You got it. So let A be an augmented matrix. Each of the following operations on A results in the augmented matrix of an equivalent system. So when we do these operations, we get an equivalent system of linear equations. You just saw in a previous example how to take an augmented matrix and write its corresponding system of linear equations, right? So now we're using those words interchangeably. Okay, are we all right? Mm-hmm. Yes or no? Yes. Okay, all right. So R sub I means row I of matrix A. Capital R sub I means row I of matrix A. So, operation. These are the 3 elementary operations that we have. These are the what?
3 operations that we have.
Elementary row operations that we have. You got it. Rows I and J can be interchanged. Whenever you say we can interchange rows I and J, we write Ri, and we write this line with the arrow on both sides, Rj. Mathematically, this means we interchange row I and row J. In other words, this means we swap the rows. It also means, in our words, we interchange the order of the 2 equations in the system. As an example, given this system of equations, or given this augmented matrix, let's say that. Given this augmented matrix, that's what we have, right? Given this augmented matrix, we have -2, 3, and 13 in row 1, 2, 1, and -9 in row 2. This notation says what? You got it. This says interchange row 1 and row 2, or R1 and R2. So what was row 1 here now becomes row 2 here. You got it. What was row 2 here now becomes row 1. You got it. Yes?
So anytime it says that, like, in, say, a question, that's basically what we do?
If it says this, yes.
Or Would there be any scenarios where it's like R3 and R4?
Yes. Yes. Yep, it's possible.
But it would have the same sign, like the arrow. Like
The arrow, this means interchange. Yep, y'all are right. This means you interchange them. What other questions do you have? So interchanging rows is a legit elementary row operation. Okay? 2, the second elementary row operation, each entry in row I can be multiplied by a non-zero constant C. We write this as C times Ri. What does this mean? This just means we take row I, we multiply it by C. We multiply all the terms in an equation by a non-zero constant. That gives us an equivalent augmented matrix. So we can take a row and we can multiply a row by a constant, which means we multiply every entry in that row by that constant.
The constant in the same row?
You said the constant in the same row?
In the same row.
We would take a row, for example, and multiply each entry in that row by that constant. So let's look at an example. So in our words, it says multiply all the terms in an equation by a non-zero constant. But as an example, let's suppose that we have this given augmented matrix. This operation says, this elementary row operation says multiply row 2 by 3. This says 3 times R2. The big arrow means this is going to give us a new or equivalent augmented matrix. Okay? We want to take every entry here and multiply it by what? 3. Do we need to change row 1? No. So we need to take 2, multiply it by to get 6. Where does 6 come from? 2 times 3. Now, our next entry. What's our next entry? 3. Good, because you're multiplying 1 times 3. You got it. Now, what is our last entry? What is our 2, 3 entry? I heard -9. I heard -27. -27? How did we get it? -9 times 3 gives us -27. Very good. So, this is an equivalent matrix here. Got it? Okay. The last elementary row operation says that row J can be replaced with the sum of itself and a constant multiple of row I. What does that mean? That means that we can take a row, multiply it by a constant, add it to another row. That's what that means. That means we can add one equation to another or a non-zero multiple of an equation. Think about elimination. Elimination, remember when we talked about an example using elimination? You want me to write up here and point it out, or you want to just finish this example first? Write and point it out. So think about when we talked about elimination, yeah? Elimination, for example, I'll get that. Elimination, we took, as an example, I'll use red. Is that all right? Okay, so this is an aside pointing out the process we did with elimination. We took, for example, we had the system 5x minus 6y equals -1. And then we had Well, let's do negative 4x plus 3y equals negative 10. And one thing that we wanted to do, we wanted to cancel out the y's. So what we did to this system, we multiplied equation 2 by 2. We left equation 1 as it was. Then we multiplied 2 times negative 4x plus 2 times 3y. I'll write that better. We have 5x minus 6y equals negative 1. Then we multiplied 2 times negative 4x plus 2 times 3y equals 2 times negative 10. Right? So whenever we're talking about our elementary row operations, to get from here to here, we did 2 times row 2. Does that make sense? No? Yes?
Yes.
Okay, so that's what we did. Now, what we did, we figured it out. So then in our system, that became 5x minus 6y equals negative 1. Row 2 became negative 8x plus 6y equals negative 21. Negative 20, right? Not 21, negative 20. Thank you. Right? And so then we added row 1 and row 2. So this row 1 plus row 2 will now get the, what? 3x. We cancel the y's equals negative 21. That's what happened with that system. Okay? So if we want to combine, we can say negative 2 times row 1. If we want to get a new row 2, we can now combine those operations, in a sense. So that's what we're going to talk about here. Row J can be replaced with the sum of itself and a constant multiple of row I. So C times row I plus row J can give us a new row J. So this says add one equation to another or a non-zero multiple of an equation. So as an example, what you'll see in your book will not write, this. That's something that I just tend to write. Point it out again. Your book will not tend to write this. I tend to write it because for me, I'm telling myself that whenever we add row 1 plus row 2, we want to get a new row 2. You can just say add row 1 and row 2. Your book implies that that last one that you write is what you're changing. So you can write instead R1 plus R2. That's what you'll see in your book. Okay? So if we have this given augmented matrix and we say row 1 plus row 2, row 1 does not change. What's changing?
Row 2.
Row 2. How are we getting the new entries? By adding what?
Row 1 and row 2.
So in the 1, 1 position and the 2, 1 position, we add them. Negative 2 plus 2 is 0. That's where this 0 comes from. What's our next one? 4, because 3 plus 1 is 4. And then what's our last one? 4, because 13 minus 9 is 4. You got it. Those are elementary row operations. Yes.
So for the aside
Good question. What the heck are we supposed to get from the aside, right? The aside, we just wanted to see that whenever you have a given system of linear equations, you can also understand what these elementary row operations are to get you from one step to the next step. That's what you're supposed to get from that.
Thank you.
You're welcome. Thanks for asking. That was the point. What other questions do you have? Okay. All right. So we talked about having a matrix in row echelon form. Bless you. Let's talk about what it means for us to have a matrix in reduced row echelon form. Reduced row echelon form just means we have our matrix is simplified as much as possible. But we have more with that. A matrix is said to be in reduced row echelon form. Typically, we'll write RREF. If we have two main things. One, if our matrix is in reduced echelon form. Okay, not reduced, excuse me. We have a reduced row echelon form matrix if one, your matrix is in row echelon form, and two, each entry above a leading one is also 0. So we've added the condition instead of below your leading ones, you have all zeros. Below and above your leading ones, you have zeros. Your row of zeros still has to be at the bottom. You got it. So, example 5. Determine if the matrix is in what? What's this? This is reduced? Row echelon form, yeah. Reduced row echelon form or? Neither. This is a what kind of matrix? Oh. Augmented matrix, yes. So now, with this augmented matrix, my question, is this in REF form or REF form or neither? REF, you said?
No, REF.
REF? You saying reduced?
No, sorry, row echelon form.
Row echelon form?
I believe it's reduced because the zeros above and below.
Oh, we have a debate. So decide. Y'all determine. Let me know.
There's a 0 above and below.
You gotta be right. 0.
It's not a trick question. It's not a trick question. What's the difference between reduced row echelon form and row echelon form?
Reduced has the 0 above and under.
Under what? Above and under each? Reduced row echelon form has zeros above and below your leading ones. That's reduced row echelon form. Row echelon form has zeros below your leading ones. So which form is this in?
Reduced.
Which one? Reduced row echelon form. Very good. This was in reduced row echelon form because on your main diagonal, you have your leading ones. You have your leading ones here. But then you have zeros everywhere else. What questions do you have? Okay, so from example 5, write the solution for this matrix. You have this matrix in reduced row echelon form. What's the solution? Go ahead. 1x equals 4. 1y equals 1. And 1z equals 8. You better believe it. So that means, so very good. So this means x equals 8, y equals 1, z equals, oh, no, you said 4. Let me write down, because you're correct. X equals 4, y equals 1, z equals 8. So in other words, you can write 4, 1, 8 is your solution.
You just multiply it to 1.
What?
Square.
You got to talk loud.
Oh, never mind.
Processing. Remember, column 1 is x. This is y, this is z. So this means 1x equals 4. 1y equals 1. 1z equals 8. Okay? All right? So now the thing becomes, whenever we have to solve, bless you, when we have to solve a system of equations using matrices, that's called, you can either use Gaussian elimination, which means you get your matrix to row echelon form and then you back substitute, or you use your Gauss-Jordan elimination and you put your matrix in reduced row echelon form so you can read off the solutions like you just did here. Okay? The thing that allows you to solve augmented matrices or a system of linear equations using matrices, the thing that allows you to do that is using elementary row operations. Okay? So that's what we're going to talk about. Yes. Well, you have to convert a system to reduce row echelon form or row echelon form? Absolutely. Yes, that's what this next example is going to do. That's what this next example is going to do. It's going to go, I'll go through and show you how to use elementary row operations to reduce. Reduce means simplify. What other questions do you have? Okay. All right. So, answer, go. We're going to use the method of Gauss-Jordan to solve the following systems of equations. Okay. So, the first thing we're going to do is we're going to take our system of equations and we're going to write the corresponding augmented matrix. That's the first thing we do. Tell me the augmented matrix by row. 2 what?
-3 and 8.
Good. We got to write that vertical bar. What's the next row?
8, 5, 8, 2.
Very good. Now, remember, whenever we're using Gauss-Jordan, we want to put our matrix in RREF in reduced row echelon form. Okay? Using elementary row operations. Okay? Now, we know that in reduced row echelon form, this first number needs to be a what? 1. How can we make this a 1? No. Think of your elementary row operations. You can do what? Divided by? So divided by, say the number, by 2. So remember, your legit elementary row operations, you can multiply a row by a constant, you can add rows, and you can swap rows. Let's remind ourselves, again, legit elementary row operations, the things that allow you to play the game, to reduce. You can swap rows, you can multiply a row by a constant, which is the same thing as saying you can divide a row by a number, or multiply row by number, you could do that. And then, so you can swap, you can multiply, you can add rows, or constant multiple over row. Okay? So, what we want to do first, we're going to do 1/2 row 1. That's going to give us a new what row? First row. Does row 2 change? No. So we just write 8, 5, and -2 for row 2. Row 1 is going to become, oh yes, sorry, go. We want, so the question is, where did the 1/2 come from? We ask ourselves, how do we make this 2 or 1? Divided by 2. So that's where the 1/2 came from. Dividing by 2 is the same thing as multiplying by 1/2. You got it. That's absolutely correct. What other questions do you have? Dividing by 2 is the same thing as multiplying row 1 by 1/2. So now this means we have to take each entry here and multiply it by 1/2. 1/2 times 2 is 1. Good. As a fraction, -3 times 1/2 is? But as a fraction, negative what? So my question, -3 times 1/2 is? What's -3 times 1/2? It's a fraction. Come on, y'all. Positive or negative? Negative. Good. -3/2. So, -3/2. And then, what do we have here? 4, because 8 times 1/2 is 4. So, what we did, we multiplied 1/2 times row 1, got a new row 1. We have an equivalent augmented matrix. So far, we have our leading 1 in row 1. Now we want to make this 8 a 0. So we can use row 1 to help us out. We can multiply, if we want to make this a 0, we can multiply row 1 by -8. Because if we multiply -8 times 1, we get? -8 plus 8 would be? 0. So let's explain it again. We want to now make this a 0. We have to write down our operation, but right now, is row 1 going to change? No, so we're just going to write down row 2, or write down row 1. Because row 1 is not going to change, so let's just write that. But now for row 2, to get row 2 to change into what we want it to be, we're going to say -8 times row 1 plus row 2. That's going to give us a new what? Row 2. So this means we multiply every entry in row 1 by -8. And in the respective column, we add the entry from row 2. So -8 times 1 is? Good. So I'll write it out as an aside. -8 times 1 plus 8. So this is coming from -8 times 1 plus 8. That's going to give us what? 0. Good. That's where the 0 comes from. Tell me how we're going to determine the next one. -8 times negative 3 halves plus 5. Good. So that's going to give us positive 24 over 2 plus 5, which is 12 plus 5, which is 17. This is 17. And then the last entry is going to be negative 8 times 4, which is negative 32. Minus 2 is negative 34. Good. Okay? And because we're at time, I'll finish recording this and make sure you watch it.
Yes, ma'am.
Okay? You got it? All right. Okay, so now where we have a 17, we want this to be what? 1. What can we do to row 2? You got it. Times it by 1 over 17. Good. So 1 over 17, bless you. 1 over 17, you're welcome, times row 2. We're going to get a new row 2. Is row 1 changing? No. So we have 1, negative 3 halves, and 4. And then row 2, because we're now multiplying each entry in row 2 by 1 over 17, you have 1 over 17 times 0. What is that? 0. Then we have 1 over 17 times 17. What's that? 1. Good. Then we have 1 over 17 times negative 34. What is that? 1 over 17 times negative 34. What is that? Negative 34 over 17, which is negative 2. Good. What questions do you have? Okay. So if I did not say use Gaussian, or if I did not say use Gauss-Jordan elimination, then you can use Gaussian elimination. You know what y is and back substitute. But here, I want you to now make this a what? 0. Good. I now want this to be a 0. How can we use row 2 to help us make this a 0 now? So my question is, what operation do we use now? That's what I'm asking. We want to make this negative 3 halves a 0 using row 2. Times, what's your it? Times row 1 by 3 over 2? Oh, multiply row 2 by 3 over 2. And do what? And add row 1. Very good. That's our operation. That's exactly what we want to do. Is row 2 going to change? No, row 2 is not going to change. So now, row 2 we write down as 0, 1, and negative 2. 3 halves times 0 is 0. 0 plus 1 is, do you need me to write the step in between? I'm saying it, but I'm not writing it. Do you want me to write it first? No? Okay, so I need your responses then. 3 halves times 0 is 0 plus 1 is 1. So this remains a 1. 3 halves times 1 is 3 halves minus 3 halves is 0. Good. 3 halves times negative 2 is negative 3. Good. Negative 3 plus 4 is 1. So how do we interpret this? X is 1 and Y is -2. Very good. That's our solution. That's our solution. What questions do you have? Yes. For Gauss-Jordan, yes. So just to repeat, the question was, do we keep repeating, or say it again? So the question was, do we keep repeating our elementary row operations until we find out what X and Y equals? Yes. The answer to that is yes if we're solving by Gauss-Jordan elimination. The answer to that is yes for Gauss-Jordan elimination. For Gaussian elimination, you just need to find out what one of the variables is and then back substitute. If you have to be familiar with both, because I may say use Gauss-Jordan elimination to solve this. If it says use Gaussian elimination to solve, that means you need to do back substitution once you find out one of the variables. What other questions do you have? Okay, so now let's do another example. Okay, you ready? Okay. So example 7, continued. This is part B. Example 7 continued. We have part B. You have the system 6x plus 2y equals -4 and -9x minus 3y equals 6. Now, when we're solving for a matrix using Gauss-Jordan elimination, our system first has to be in what form? Augmented matrix, but in order to write down your augmented matrix, your system has to be in what form? Standard. Good. So we first have to make sure our system is in standard form. Standard form means we have our equations simplified with the variables on the left, constants on the right. So, is equation 1 simplified? No, because they all have what in common? 2. So we're going to simplify it by dividing equation 1 by 2. That equation then becomes what? Good. Equation 2, is that simplified? No. They all have what in common? Just a 3? You want to deal with negatives? No? So instead of 3, they have what? -3, yes? So divide everything by -3. What does equation 2 become? 3x equals -2. These equations are what? The same. These equations are the same, right? So how many solutions do you expect to have? You're very good. Infinitely many. Yes? You expect to have infinitely many because the equations are the same. We talked about solving systems before. So you know that that's why you're able to say, if the equations are the same, you have infinitely many solutions. The thing is, what does that look like whenever we're solving an augmented matrix then? Whenever we're doing that, that means we're going to have a row of zeros at the bottom. So now let's just write down and confirm what we will have. So we start out with we have our matrix, we have our system in standard form, so now we can write our augmented matrix. Good. Tell me what it is. The same thing. Good. What's the size of this matrix or the order? You said 2 by 3? I heard 2 by 3, 3 by 2.
2 by 3.
2 by 3 because we have to have the what by the what? Rows by the columns. You got it. 2 by 3. The order is 2 by 3. Good. So What we want to do, there are a couple of approaches. What do you want to do first? Our goal is to put this in what form? Use Gauss-Jordan elimination to solve. So we want to put it in what form? Reduced what? Good, that's what we want. We want reduced row echelon form. How are we going to get there? What do you want to do? Can't hear you? Want the 3 in the 1-1 position or the 2-1? In the 1-1 position, we want it to be a 1. So what do we need to do? Multiply what by 1/3? Just 3? The whole row 1. You got it. So we're going to multiply row 1 by 1/3 to get a new row 1. Is row 2 going to change? No. So row 2 is going to be 3, 1, -2. Now 1/3 times 3 is 1. What's the next one? Good. 1/3 times 1 is 1/3. What's our next one? Can't hear you? 1/3 times -2 is? Good. Both of you. You got it. Good. Now what do you want? We want what? Use your position numbers. Or tell me where it's located. You want the number? We want the row 1, column 1. That's this one. You want row 2, column 1. You want this to be a 0. We want the entry in the 2-1 position to become a 0. I believe you. I'm with it. How do we get this to be a 0 now? How do we get there? -3 times and add row 2. You got it. -3 times row 1 plus row 2 to get a new row 2. You got it. Is row 1 changing? No. So row 1 we're going to write down is 1, 1/3, and -2/3. So now -3 times row 1. So -3 times 1 is -3 plus 3 gives us 0. Good. The next one is -3 times 1/3 gives us -1. -1 plus 1 is 0. Good. Then our next one is good. -3 times -2/3 is 2. Good. And 2 plus -2 is 0. Good. This confirms what we talked about before. You now have your row of zeros at the bottom. This is in reduced row echelon form because we cannot make this 0. So how do we interpret that now is the question. So this is now, we write the corresponding equation for row 1. Remember, column 1 represents X, column 2 represents Y. So this is the same thing as X plus 1/3 Y equals -2/3. If we do not want fractions, we can multiply the entire equation by 3. Good. So that's going to give us 3 times the quantity X plus 1/3 Y equals 3 times -2/3. So that gives us 3X plus Y equals what? Negative 2, good. And then if you want to solve this, at this point you either want to solve it for x or solve it for y. If we're solving for x, you could have just solved here. If you want to eliminate the fractions, this is what we do. We can solve for y and get y is negative 3x minus 2. We know we're going to have how many solutions? Infinitely many. Good. We decided that at the beginning when we started because they have the same line. The equations represent the same line. So remember, with infinitely many solutions, we write a set with an ordered pair. We know y is this, so we have to write what in our first position? That's y. What's our first coordinate? Say it loud. X, yes. It's x, comma, y is negative 3x minus 2, such that x is a real number. This gives us our solution here. The set of all points x, negative 3x minus 2, such that x is a real number. Okay? Questions?
How did we start? How did we get the 3? But we started distributing the 3.
Here,
The second equation is.
we multiplied 3 times x. 3 times 1/3 gives us 1.
How did we get that 3 on the outside?
We wanted to eliminate the fraction. So if we want to eliminate the fraction, to eliminate the fractions, we multiply both sides by 3. What other questions do you have? Okay, the last page is just practice. So make sure you do that on your own. It's mainly making sure that you're comfortable filling in the blanks by performing row operations. Okay, have a good one. Next class will cover 9.3, 9.4, and possibly 9.5. Okay, have a good one. Now let's do a couple of practice problems. So fill in the blanks by performing the indicated row operations. So here we have this augmented 2 by 3 matrix, 2 rows, 3 columns, and we want to perform the indicated row operation negative 3 row 2 plus R1 to get a new R1. So in your books, remember, this would just appear as 3 row 2 plus row 1, which means that what you're ending with is the row that's changing. Okay, so row 2 is not going to change, so we're going to write 1, 3, and 5. Now, for negative 3 row 2 plus row 1, we're going to do negative 3 times row 2, so negative 3 times 1 gives us negative 3. Then we want to add row 1, so in that position move up, negative 3 plus 3 gives us 0. Okay, now negative 3 times 3 is negative 9. Negative 9 plus 2 is negative 7. Then negative 3 times 5 is negative 15. Negative 15 plus a negative 7 is negative 22. So that is our matrix. Okay, now we have what size matrix here? Augmented matrix. It is 2 rows, 1, 2, 3 columns, so it's a 2 by 3. Now, the operations, we have 1/2 times row 1 to get a new row 1, or 1/3 row 2 to get a new row 2. Remember, your book would just have 1/2 times row 1, and it would have 1/3 times row 2. Same thing. So let's do it. So we need to multiply each entry in row 1 by 1/2. So 4 times 1/2 is 2. 2 times 1/2 is 1. 2, or 1/2 times -8 is -4. That's row 1. Row 3, we need to multiply each entry by 1/3. So 3 times 1/3 is 1. 1/3 times -9 is -3. And 1/3 times 0 is 0. There you go. Have fun. Do your homework.